So thank you very much, Sandy, and welcome everyone. Good afternoon. So today I would like to talk to you a little bit about this emerging field of federated analytics, which is something that I have been paying very close attention to, and I think there are exciting developments that are coming up every week, every month as I soon. So I've been following that track closely. So we'll talk a little bit about what it is, the challenges it's aimed at solving, and give some motivating questions, let's say, on what's required to make it a reality for more and more organizations. So I typically like to start with just a review of what the analytics workflow looks like, your typical workflow for working in this field. So usually start with the analytics design phase, which is when the data scientist is kind of understanding the business problem to be solved, framing it as an analytics problem that a model can help address, identifying the different data sources, doing data exploration, identifying what are the types of models, the families of models that would be well suited. Then once that part is done, then they'll typically move to the phase where you're training the model with some historical data that it's available. And you're testing the accuracy. You're trying to figure out how well it does on the task that you want on past historical data. And once you're happy with what you've got, you typically deploy it to what we call the inference phase, which is when you're using it to make predictions, to score new data that comes in. And as more data comes in and you keep making predictions, then you have the opportunity to actually keep retraining your model because you have not only more data available, but you also may have your underlying phenomena changing over time. So it's very important to keep monitoring performance and keep updating models as you progress. And one key thing about this entire process is how the continuous nature of learning. The fact that data scientists will design, it's very iterative, and data scientists will design and test multiple models at the same time. Once the model gets deployed, you continue to retrain to keep it up to date, and eventually more data sources become available, your model performance degrades enough that you need to go back to the drawing board and redesign, or perhaps new techniques come up that you want to try out, and you go back to the design phase. And all of these feedback loops are super important for the success of any analytics use case. So now if we go and take a look at the infrastructure where this process is happening, we're going to see that it's actually very complicated and convoluted. If before your cores were residing in a big data center, more and more, you have your data and your compute resources moving to the edge, to the cloud, and so on. And then if you take an X-ray of that infrastructure and look for where your data is, you're going to see that it's no longer in a big data center, but you actually have centers of data that are spread all around. And it can be really hard pulling that data into a single location. It can be really difficult tapping into data that it's in these different pockets. So if you think about how are we going to handle this and the architecture for how this happened, historically, this architecture has been shifting between centralized to distributed back and forth. And more recently, when cloud emerged, we thought perhaps for a brief moment that we're done, everything is going to converge to the cloud. That's where all the model building is going to happen. We have these huge compute resources, and that's how everything is going to be done. But then the IoT wave came and kind of brought back the spirit of decentralization of distributed analytics. So thinking about the model training, model building perspective, looking from that angle, let's think about how we could go about handling that dispersed data that we have in the infrastructure. One way would be the traditional centralized approach, which is quite common and supports really well several use cases. So the idea is you're going to pipe all the data you have into a big repository, and that's where you're going to create your models. That's where you're going to get your historical data on, and you have the big compute resources to train big, deep neural networks and so on, which is a good approach if viable. But there are many different factors that can prevent you from doing things like that. A few of them relate to that data distribution we have been talking about. So the fact that the data is inherently dispersed, and those relate to your IoT effect, that it's pushing your data collection and really at many times your compute resources more and more to the edge, so you have that decentralization. You have a multi-cloud effect with enterprises these days having data spread into 6 to 10 different clouds at a time. And you also have your traditional data systems in the mix, so your data warehouses, your ERPs, and so on. So data is inherently dispersed across these different systems. And it can be really difficult to move due to things such as your bandwidth constraints. So it's the actual engineering problem of moving huge volumes of data to a central location in data that it's generated in a very fast speed, such as IoT data, for example. You may have regulatory constraints on what data can be moved across certain geographical boundaries, certain organizational boundaries. So you may have regulations preventing you from moving data at all with privacy concerns. And last but not least, you have also your security concerns with the actual data movement. So if you have a few of these constraints on your use case, and centralizing everything is really not an option, then what can you do? You could go all the way to the other side of the spectrum and go distributed all the way. So the idea is you're not going to move the data to a central location. You're going to leave it where it is, and all the analysis is going to happen in isolation in these different data pockets. So in that way, you do away with all of your problems with moving data. You're not going to run into those barriers because you're not moving. But you need to be mindful that the amount of data that it's going to be used to train models in these isolated pockets, it's actually going to be much less than what would have been if you're able to join everything into a central location. And it's not just about the amount of data itself, it's also about diversity. If in each of the pockets is only going to be able to learn from the history of the data it possesses. And for many use cases, and we're going to talk a little bit about use cases soon, there could be advantages in collaborating and in actually having access to a wider and more varied data set. So that brings us to, oops, a little bit too quick here, but that brings us to federated analytics. It's the idea of trying to sit in the middle between centralized and distributed, where you do some of your training in a distributed way, close to your data sources, but then you continue to iterate and share model parameters only and not raw data to create models that are aimed at the global data set. And the advantage, I don't think my animation worked very well, I apologize, but think we're going to go into a little bit more detail and think that the advantages here is you're avoiding explicitly sharing raw data, and also the model parameters in general tend to be smaller than the raw data used to train models. So you're passing, in many situations, not always, but in many situations, you're passing less data through the network to do something like that. So that gets at your bandwidth problems and your challenges with privacy. So let's think about a few just motivating use cases. We talked about the structure. So what are some example scenarios where this type of thing helps, like this paradigm for federated learning? Think about user device type of use cases, such as wearable devices for healthcare, for health monitoring, or maybe mobile phones. In these cases, you're running models in all of these devices, and the providers have a lot of interest in continuously improving the models that get deployed. But this type of data tends to be very, very private. It has to do with your maybe metrics about your blood pressure, or your health, biometric data. Or maybe it's your text messages and your photos that are residing on your phone, all very private. None of it can be pulled off of the device into a big cloud instance to get to a very big data set for training. So if you don't have any way of doing some training on that data, what you're left with is probably some data that you're able to centralize, but that it's biased to the data you were able to collect, and that it's not really as close to the deployment data as you would like it to be. Other examples have to do with predictive maintenance. For example, if you're trying to use sensor collected data from the operations of a piece of equipment to find patterns that are lead indicators that piece of equipment is about to fail. If you try to do something like that and you're in the equipment manufacturer, you would have a lot of advantage from being able to run this type of use case on data for the actual users, rather than just test data that you did in your labs when you're building that piece of equipment. So you want to deploy that into industrial manufacturing, to perhaps oil drilling and so on, and actually see the patterns of behaviors. But those sensor reads sometimes contain some very private information from your clients and their operations that they wouldn't be willing to share with you. So it's another situation where you might encounter these barriers, and you have a lot of advantages of being able to do your analytics in a different way. So just a recap on perfect conditions. I also had clinical research there. It's the same idea as with the wearable devices. You have some clinical data from patients that you don't want to share across different institutions, but those institutions might be wanting to collaborate in clinical trials and in developing new drugs and so on. So the key conditions that we're looking for here, where federated analytics helps, are when you have data that is inherently distributed. You think there's a good chance for information gained through collaboration. You have advantages of training your models on deployment-specific data that you otherwise wouldn't have access to, such as in the cell phone space, for example. You have very large data volumes. You have concerns with privacy, and so on. So going into just drilling down a little bit, and it's going to be quick, on how this actually works. I'm going to focus on one famous algorithm for this, which is federated averaging. As a caveat, it's not the only one, and the reason I selected it for today, just to go over, is so it's because it is a very popular and very famous one, and I think the overall idea is simple enough to go through in a quick presentation. So imagine that you're trying to train a deep neural network, and you're sitting at an initiating node somewhere, and you have data that is spread around other nodes. We're just going to call them your local nodes. Then the way this works is that the initiating node has the topology of the network to start with and some initial weights, and it will share these weights with the data zones, with these different, I'm gonna call them nodes, so with these different nodes, so that they can do a round of training locally based on their own data. Then they're going to come up with an update suggestion for the weights. And these update suggestions are going to be different. That's why you have different colors there, because they're going to be based on the different local data residing in each of these locations. Then these weights get shared back with the initiating node where they're averaged to come up with one synchronized weight for the entire system again. Then the next step is to broadcast this back to the local nodes where another round of training is going to happen again. It's a second epoch, we can call, and you're going to have these new set of weights that are going to be shared again and average again, and so on. And this process is going to iterate until convergence. So you can get to really good models this way, but it's not without its challenges. One of the things to think about is the fact that you have what we technically call non-IID data, so it's not independent, identically distributed, so it doesn't work as well as in distributed computing. When you can divide your data sets in chunks of equal size, you're going to have data zones that are naturally different, that have naturally different sizes. You can still have problems with your communication efficiency if it takes a lot of those cycles to converge, and if your models are very big, it might still take a long time. You may have issues with stragglers and dropouts if you are in a communication constrained environment where some of those nodes are not getting back to you. And you might still have some concerns with privacy, because even though you're not explicitly sharing raw data, it is known that you can sometimes glean information about the underlying data that generated deep learning models. So those are all things that there's a lot of research going on for all of these aspects related to federated analytics, because it does overcome a lot of challenges and unlocks the potential for many different use cases, but those are always all things that we need to be mindful of. And from let's say an engineering and an infrastructure perspective, we need to think about how are we going to actually make this coordination work? How can we address the data that it's necessary, ensure that the compute resources are there, ensure transparency across this process and the coordination. So I just wanted to leave you at the end with these thoughts on how can we actually make this real and make this entire process and this entire workflow work for a variety of use cases. So thank you very much for your time today. And thank you.